Today we're going to start 3.2 logarithms and their graphs, but before we begin, we're going to review last lesson where we graphed exponential functions. So I have again our function 2 to the x power. We're going to fill out a table and graph it. So we are going to evaluate -2. So 2 to the -2 power, remember, is just 1 over 2 squared, which is 1/4. 2 to the -1 power is 1 over 2 to the first power, which is 1/2. 2 to the 0 is 1. 2 to the first power is 2, and 2 squared is 4. So if we go ahead and graph this, we get -2 and then 1/4, -1 and then 1/2, 0, 1, 1, 2, and 2, 4. So here is our function 2 to the x power. All right, so if we were to explore what this looks like as an inverse, let's go ahead and find the inverse of this function. So remember, we find the inverse, we replace f of x with y, and then, oh my goodness, and then we will switch our x and y values. So we have x and then 2 to the y. And we have to think about a way, how can we get this y by itself? So now y is in the exponent position. So we need a new operation that will help us to remove an exponent in this exponential expression. So we have a logarithm function, which is defined as exactly that. So the logarithm function would take our same base and this exponent and rewrite it using this new function form. So we have this base of 2 and we have this exponent of y. Change colors here, exponent. And so what the logarithm function will, how it will rewrite it, we will take log, and the base will be the same as our original exponential expression. So the base would be 2. And then we're taking the log base 2 of whatever value we had here by itself. So that will just be x. And it's going to equal our exponent of y. So the base of the exponent is still the base of the log, and the solution of our logarithm expression will be our exponent. So now if we think about how we can rewrite the inverse of this function, we can say that our inverse would be f to the -1 x, and then it would be log base 2 of x. So our logarithm function is the inverse of an exponential function. So let's just graph this. I'll go ahead and fill out my table. So log base 2 of x. And we're going to spend more time actually graphing these functions next time. But I'd like for you to see visually what the function looks like and how it behaves, so that when we're working through some of the problems, you have that good foundation. So if you remember, when we're graphing an inverse function, we can take the original function and then we just switch our x and y coordinates. So if we replace our x values here, I'll use my y values from our table above. Whoops, that's going to be 1, 2, and 4. And then my f of x will be my f to the -1, my inverse function, will be the x values. So our domain and our range just switched. So I'll graph this in a different color on the same coordinate plane so we can see that relationship between our exponential function and the inverse function, which is log. So we have 1/4 -2, 1/2 -1, 1, 0, 2, 1, and 4, 2. And you'll notice with our exponential function, I did not write it, but we did have this asymptote happening at on asymptote horizontally happening at y equals 0. And now we can see our asymptote will be vertical at x equals 0. All right, so this is our inverse function, which is our log base 2 of x. So what we're working with today is we're going to look at how to evaluate logarithm functions and expressions and looking at some of the properties of log. So just based on what we know so far, we're going to just rewrite and evaluate some of these expressions given what we have defined our logarithm as up here. So again, the base of our exponential expression is the base of our log, and the answer is our exponent. So when we're evaluating, it helps us to remember how to rewrite these expressions, and it also helps us to remember the properties of exponents. So one way that you can evaluate this logarithm expression is we can replace our f of x with just y, and that kind of helps us when we're rewriting this in exponential form so that we don't have to worry about having f of x. So we're evaluating 32. So I'm going to replace my x with 32. And I have log base 2 of 32. So I'm going to rewrite this logarithm expression as an exponent. So when I'm writing it as an exponent, remember the bases are the same. So my base would be of my exponent would be 2. Remember the value that the logarithm expression equals is going to be my exponent, and it will equal, the exponential function will equal 32. So when I'm solving this type of equation, what is helpful is to get my bases to be the same. So I know I can rewrite 32 as 2 to the 5th power. And so the only way these two sides of the equation would be equal is if my exponents were the same. So in this case, we would say this equals 5, or we could just say log base 2 of 32 equals 5, because we're trying to evaluate this original expression. So let's go ahead and have you pause the video and work through 2, 3, and 4, and then we will work through those answers together. So hopefully you've had a chance to try 2, 3, and 4. Now we'll check our answers. So we have y equals log base 3 of 1. So I can rewrite that as 3 to the y power equals 1. We know that an exponent raised to a 0 with any base will always yield a 1. So in this case, we would say y equals 1. So we remember y to the, 3 to the 0 power is 1. That's kind of this exponential rule that we remember to get log base 3 of 1 equals 0. For number 3, we have log base 4 of 2. So we can rewrite that again, 4 to the y power equals 2. And again, we want those bases to be the same. So we can rewrite 4 as 2 squared. And then we would multiply our exponents, and that would equal 2. So 2 has an exponent of 1. And so now, again, I know that in order for these two sides of the equation to be equal, the exponents have to be the same. So I would say 2y equals 1, and then I can just solve for y. So this expression log base 4 of 2 is just equal to 1/2. And then our last one, number 4, we would say log base 10 of 1 over 100 is y, and we can rewrite this as 10 to the y power equals 1 over 100. And I like to think about things, you could turn this into a fraction, but I like to kind of get my fraction into a regular number. So I'm going to rewrite this expression using a negative exponent. So I'll say 10 to the y is 100 to the negative 1. But again, I want, stray mark there. Again, I want the bases to be the same. So instead of writing 100, I'll replace that with 10 squared. And then remember, I'm multiplying those exponents. So that would be 10 to the negative 2. So now I know that I have the same bases. I have equal sides. So I can say that y is equal to -2, or the log base 10 of 1 over 100 equals -2. So we have our properties, some of the properties of logarithms in our summary table here. So some of these we kind of noticed as we're working. We know that any way for our logarithm, so a logarithm of a of log base a of 1 equals 0, because if we rewrote this as an exponent, a to the 0 power would be 1. We know if we have the same, if we're evaluating the logarithm with the same value base, we know these essentially are going to be canceling out. So we can see that a to the first power is just a. So we would say this expression always, always, always will equal 1. And that kind of follows number 3. We have the log base a of a. We know that portion equals 1. So this entire expression would also equal whatever we're trying to evaluate. In this case would be our exponent of x. So we could rewrite this as an exponent and see a to the log base a of x is just going to be equal to x. And if we have two logarithm expressions with equal bases, we know that whatever we are taking a log of is also going to be equal. And that kind of reminds me of our rule that we've been using for our exponents. We want those bases to be the same so that the exponents have to be equal. So we're going to practice using these properties of logarithms for the next few examples. So why don't you pause the video and give these 4 problems a try, and then we will go over your answers. Hope you've had a chance to work through 1 through 4. So now we'll go over them together. So for the first one, we can see that they have the same base, same expression. So we know that x is just going to equal 3. For number 2, we have log base 4 of 4. So we know that this expression evaluates to just get 1. So x would equal 1. Similarly, on number 3, log base 5 of 5, we know this expression evaluates to 1, so we're left with just x. And for number 4, 7 to the log base 7 of 14, 7 to the log of 7, since they have the same base, we know that it will just evaluate to get 1. So 1 times 14 will be 14. So natural logs is just a logarithm with a base of e. So we just give it a different name and we write it in a different way. So you'll notice if you just have ln, that means natural log, which is really just our logarithm function with a base of e. So because natural log is just a regular log function with a special base, all of the properties of our log function are also true for natural log functions. And let's go ahead and try using some of those properties down below. So we have 4 problems. Go ahead and pause the video and try rewriting them using our properties of natural log, and then we will go over those together. So hopefully you've had a chance to work through 1 through 4. So if I start on number 1, the first thing I'm going to do is rewrite this as an exponent. Oh my goodness, it's not 6, it's e. So we know that this will equal y. So I'll just say this is log base e of 1 over e equals y. So if I write this as an exponent, I get e to the y equals 1 over e. And because I want the bases to be the same, I'm going to rewrite the right-hand side using a negative exponent, which will be e to the -1. So here I can see that in order for these two sides to be the same, they have the same base, the exponents must also be the same. So what this means is the natural log of 1 over e is equal to -1. For number 2, we have e to the natural log of 5, and we remember that natural log is just log base e. So we can see that this portion of our expression will just cancel out to be 1. So we can just say that's 1, and our answer will be 5. For number 3, we have 4 times the natural log of 1. So natural log of 1, if we remember what that means log base e of 1. So we know that e to the y will equal 1. And the only way that is possible is that if y is 0. But that's our first property up here. that if we have natural log of 1, it's always going to equal 0, because we kind of just reviewed why that's true off to the right side here. So natural log of 1 is just 0. So 4 times 0 will be 0. For number 4, we have the natural log of e times 2. So we know the natural log of e is something I'll just cancel out to get 1. So 1 times 2 will be 2. All right, so on your homework practice, you will be working with the properties of logarithms and the properties of natural logs. You're going to practice writing them in exponential form and writing them as log expressions. And you're also going to practice evaluating logs on your calculator. So just one thing to remember, depending on your calculator, of course, you should have a couple of buttons that relate to logarithms. So you'll have a log button. And remember, this means that your log is only of base 10. So if we ever have log just by itself, that indicates that the log base is 10. And then you might have a natural log button, and we know that that just means that you have a log base e. And so when you're evaluating, just keep that in mind when you're evaluating on your calculator, that this log button is only dealing with that base of 10. And so after looking through your homework problems, it looks like you're just going to be evaluating natural logs in your calculator. So they give you an expression, and you're just going to be using your natural log to evaluate whatever they give you in your homework practice.